Welcome to Lecture 8, Dot Product and Moment of a Force about an Axis. In this lecture, we'll be discussing the dot product, the moment of a force about an axis scalar analysis, and the moment of a force about an axis vector analysis. Along with the cross product, another useful vector algebra tool is the dot product of two vectors. We also call this the scalar product because the result is going to be a scalar. So let's consider two vectors, A and B, with an angle theta between them. We say that the dot product of A and B is read as A dot B, and we write it as A dot B, with this dot being read as dot, not to be interpreted as a multiplication sign. And A dot B is equal to the product of the magnitudes of A and B and the cosine of the angle between the two vectors. So we'll show that in equation form here. So A dot B is equal to A times B times the cosine of theta. Now notice that this is a scalar, it's not a vector. It can be positive or negative. And notice that we're now using the cosine between the two vectors, whereas with cross product we use the sine. Also, take note that unlike the cross product, A dot B is equal to B dot A. Let's first look at the dot product with regard to our Cartesian unit vectors I, j, and k. Since the dot product equation involves the cosine of the angle between the two vectors that are being dotted together, when we dot any two different Cartesian unit vectors, the result will be zero because those vectors I, j, and k are orthogonal. Is 90 degrees between each of them. So the cosine of 90 is 0 degrees. The other three combinations of the unit vectors where we dot a unit vector into itself, the result will be 1 since the cosine of the angle between a unit vector and itself is 1 since the angle is 0. So this makes dotting two general Cartesian vectors together much easier than when we found the cross product of those two vectors. So when we dot two general Cartesian vectors A and B together, it's going to yield these three terms. Now notice they're all scalars, and they're just going to be numbers that add together and result in a single number. The number might be positive or negative, but it's a scalar. Let's look at a couple of applications of the dot product that we can use in statics. The first one is we can use the dot product to find the angle between two vectors. If we solve our dot product equation for theta, we get this equation, which we can solve for theta, which is that angle between the two vectors. We can also use the dot product to determine the components of a vector parallel and perpendicular to a line. This is a general line, but it could be a specific line such as one of our three axes. So let's consider vector A in the figure here and line AA. And I think we can see that the magnitude of the component of A along the line AA is going to be equal to A cos theta, nothing new there. And the vector A sub A would be the magnitude of that component along the line times a unit vector in the direction of A. We've established that the component of A, vector A, that is collinear with the line AA is vector A sub A, and we know that the magnitude of that vector is equal to A cosine theta. Now notice how close A cosine theta looks to the right side of our dot product equation. So let's make it look like that. I'm going to stick a B in here for now and write that AB cosine theta is equal to A vector A dot vector B. Now I can't just put B in here without worrying about my equality, but if I force B to be 1, then I've maintained that equality. So if I force vector B to be a unit vector, then its magnitude is going to be 1. And for this application, I'm going to let that unit vector, which I'm calling B, be a unit vector along the line AA, and call that unit vector A. So the result we have here is I've maintained this equality. I've maintained this equality, so I can say that the magnitude of the component of vector, the original vector A along the line AA, is equal to vector A dot the unit vector along the line AA. Once we've calculated A sub A using the dot product that we established on the previous slide, we can then write that vector component in Cartesian form, since we now have its magnitude and a unit vector along its line of action. Now remember that when you calculate this magnitude, the dot product is going to yield a scalar. It could be positive or negative. If that scalar is positive, then that means that the vector A sub A has the same sense as the unit vector that you used. In other words, is going in the same direction as the unit vector. And if that dot product, the scalar, turns out to be negative, then it's going to act opposite to the unit vector that you used. Now let's look at the moment of a force about an axis using scalar analysis. Consider the situation shown here in the figure, which is probably a situation most of us are familiar with. We're using a simple lug wrench to try and remove a lug nut that is one of the lug nuts securing a rim and tire to an automobile. Given the geometry of the situation shown, a moment about O, this moment here, is created by F being applied at a perpendicular distance D from the lug nut, point O. So this is a right angle here. And the useful component of that moment is going to be along the y-axis, which is the axis that the lug nut rotates around. What's not shown here is there's also a component along the x-axis, which is not useful. This would be m sub x. This moment is not useful, and if you've been in this situation, it can be quite frustrating, and you would usually counter the effect of that moment by putting your hand or foot or something here at this location on the lug wrench when you're pulling on the end of the lug wrench. The moment about the y-axis can be calculated by F multiplied by the perpendicular distance of F from the y-axis. Okay, so now I've got a right angle here and a right angle back here. And that distance we'll call d sub y is going to be equal to d times the cosine of theta. So the moment about the y-axis, which is F times the perpendicular distance between the force and the y-axis, is equal to F times d cos theta. So in general, for any axis, the moment of a force about that axis is going to be equal to the force times the perpendicular distance between the force and the axis. The perpendicular distance between the force and the x-axis is this distance over here, which is, we'll call d sub x, and that's going to be equal to d times the sine of theta. Now let's look at the moment of a force about an axis using vector analysis. We're going to use the same setup with a lug wrench being used to loosen a lug nut, and same figure, same geometry. We can see that the moment about the y-axis is the projection of m sub o onto the y-axis, and we can now use what we learned about the dot product to calculate the magnitude of the moment about the y-axis. So we find that magnitude by taking a unit vector along the y-axis, which is j, and dotting that with m sub o. And from the previous lecture, we learned that m sub o equals r cross f. Now, you need to note that when we're dealing with the force, the moment of a force about an axis, that O can now be any point along that axis. So that makes R a position vector from any point along the y-axis, for this case, to any point along the line of action of the force. So make sure you take note of that. And we cross that position vector into the force F. So we're going to write that. We're going to substitute R cross F for m sub o, and we end up with J dot R cross F. Now this is also known as the scalar triple product. In general, for any axis A, we can find the magnitude of a moment about that axis by taking a unit vector along that axis and dotting it with R cross F. Now let's write that previous equation that I've shown again here. Let's write that in Cartesian form. So the unit vector becomes expressed in its I, J, and K components, and R cross F we can express as a determinant. And if we perform those calculations, the result is this long expression here. And remember that all this is going to simplify down to a single number. It's a scalar, and the number may be positive or negative. We can also write this expression here in terms of a single determinant, where the first row of the determinant is going to be the x, y, z components of the unit vector that we're using. The second row of the determinant is going to be the x, y, and z components of the position vector. And remember that the position vector can be from any point on the a-axis, our general axis, to any point on the line of action of F. And the third row being the x, y, and z components of F. Once you've determined the magnitude of the moment about the specific axis, you can then write the moment about the axis in vector form, since you have the magnitude and you have a unit vector in the direction of the axis. Now remember, when calculating m sub a, it's going to turn out to be a number, it's a scalar, and it could be positive, which means that the moment has the same sense as u sub a, and it also could be negative, which means that that moment is acting opposite to u sub a.